Now, the learning objective here is about properties of acids. What is an acid? There are several definitions of acids. It could be H plus donors, meaning proton donors, or they could be defined as those that have a sour taste, like vinegar has a sour taste due to the presence of acetic acid, which is CH3, COOH. I told you that gives you a weak electrolyte. Or even citrus fruits, which contain citric acid. Okay, so I think the sour taste is characteristic of a presence of an acid, but we'll see more definition soon. The acids cause color changes in plant dyes, which is why people use blue litmus paper to determine if a solution is acidic. It contains pigments from the plant. Okay, acids react with certain metals to produce hydrogen gas. There's fizzling like you see there. Production of a gas during a reaction is evidence of a chemical reaction happening. So if you take magnesium ribbon and react it with hydrochloric acid, you're going to get magnesium chloride, which is soluble aqueous. It's not a precipitate, and hydrogen gas lost in air. Okay. Acids also react with carbonates and bicarbonates to produce a gas, but in this case, the gas is carbon dioxide. When acids react with metals, you're going to get hydrogen gas. When they react with carbonates or bicarbonates, you're going to get carbon dioxide. For example, here, hydrochloric acid reacting with calcium carbonate gives you calcium chloride, which is soluble, plus carbon dioxide and water. Aqueous acid solutions usually conduct electricity because they give strong electrolytes. They form strong electrolytes in water. They form lots of ions. For example, HCl in water is going to give you H3O plus Cl minus. This H3O plus can just be taken as H plus. Next, properties of bases. These ones will have a bitter taste. They feel slippery like your soap, bar soap. They contain bases. That's why soaps slip out of your hand in the bathroom, or if you step on it, you're just gonna be down on the floor within a second. You'll slip and flow. They cause color changes in plant dyes. Talking about red litmus paper, it will turn blue. When you put a drop of a base solution on red litmus paper containing plant pigments, it's going to turn blue. And then aqueous base solutions usually conduct electricity, especially of strong bases. We already did the part or the subtopic on electrolytes, and we said sodium hydroxide is a strong base. It gives you lots of hydroxide in water and lots of Na+. Okay? And we said strong electrolytes are those that are formed from ionic compounds that completely dissolved in the solvent like water. So the first definition of acids and bases will be based on Arrhenius, the scientist's definition. So Arrhenius said that Arrhenius acid is a substance that produces H plus in water. So you're looking at HCl, this is Cl, and that's your hydrogen, and this is your water molecule with 2 lone pairs here. So what happens is that one of the lone pairs of electron will take away this hydrogen from here, and these 2 electrons will be given to the chlorine right now has 3 lone pairs. So it's going to end up with 4. Now remember that the valency of chlorine is 7 because chlorine is in main group 7. You get a chloride with a negative charge because there's an extra electron, so this will be negative. The oxygen is going to have a lone pair, and because now he has 3 hydrogens, formal charge is positive. We call that hydronium. So according to Arrhenius acid is a substance that produces hydronium in water. or produces protons. H plus is a proton, a hydrogen without an electron. On the other hand, Arrhenius base is a substance that produces hydroxide in water. For example, if you have NaOH and you put it in water, it's going to give you Na plus and the hydroxide portion of it. So this is what Arrhenius is defining as hydroxide. And because it's formed, that means that this sodium hydroxide is indeed a base. So here you're looking at hydronium ion, which is just the H3O plus. Alternatively, we can draw it like this, with a lone pair and a plus charge. Of course, dipole moments will point towards the oxygen, making the oxygen electron rich. These hydrogens will be acidic, oxygen partially negative, which is why you see this area right here is very, very orangish. That's telling us this is where the electrons are mostly found. And then the positive charge will be somewhere in the middle of the molecule, denoted by the blue area. So this is an acid because it has lots of blue area in the model. Bronsted acids and bases. So we say that Arrhenius defined an acid as a substance that produces H3O plus or H plus in water. Another scientist called Bronsted has his own definition of acid and base. Arrhenius defined the base as a substance that produces OH minus. So what will Bronsted say about the base? What will Bronsted say about the acid? So Bronsted said that an acid, now called Bronsted acid, is proton donor, one that gives H plus or H partial plus given out. It means that the species that gave it out is an acid. And then a Bronsted base is one that accepts that H plus that was given. So this is H plus acceptor, or you can call it H partial plus acceptor. So when someone gives, another person has to receive, right? So which is what you are doing here. So an example is given of ammonia. Ammonia has a lone pair. So it's showing here that it's reacting with water, and ammonia is gonna use the electrons. That arrow means that you're making a bond between the nitrogen and the hydrogen, and the bond is made of two electrons. Which ones? These ones that are lone pair. So nitrogen is still in that hydrogen, and these two electrons in this bond will be put onto the oxygen. So assume that this is the hydrogen that was stolen. The two electrons on nitrogens now is a bond, and then you have the resident hydrogens. This nitrogen with 4 bonds, if you try doing the math, 4 more charge, you get a plus charge on it. The oxygen now has 3 lone pairs and a bond. So there is an electron here that came from the oxygen. So those are 7 valence electrons. So we put a negative here, or do the 4 more charge, you'll see that oxygen has a negative charge. So this tells me that ammonia right here accepted a proton. So ammonia is proton acceptor. And if it's a proton acceptor, ammonia is gonna be the base. He accepted a proton. On the other hand, the water gave out this hydrogen. That hydrogen is donated. So this is the hydrogen is partially positive. So this is a proton donor. So water is playing the role of an acid. Okay, so this played the role of an acid by giving away the hydrogen, and this ammonia played the role of a base by accepting the hydrogen. It's right here. It was accepted. The water lost the hydrogen. Using the second arrow, we are breaking the bond to give you the hydroxide. Now, Arrhenius defined a base as that which dissolves in water to give you hydroxide. Bronsted here is saying a base is that which accepts a proton, which is what ammonia did. Ammonia accepted a proton, water lost the proton, water plays the role of an acid, ammonia plays the role of a base. Down here it says that a Bronsted acid must contain at least one ionizable proton. What is ionizable proton? If you look at water, these dipole moments we learned about, this pointing the oxygen. Oxygen is partially negative, hydrogens are partially positive. Because of the partial positive charge, we say that these hydrogens are partially ionized, and therefore water qualifies to play the role of an acid because he has at least one ionizable hydrogen, the one with partial positive charge. Another example is HCl. Dipole moments point towards the Cl, meaning the hydrogen is less of electron density, it's partially positive. Chlorine is full of electron density, is partially negative. So again, HCl then is an acid. Okay. This table shows you some types of acids. Those that give one hydrogen are called monoprotic. Give or donate one hydrogen or one H plus or one proton. Those are monoprotic. 1, 1, 1. Those are the acidic hydrogens to be given out. You see, only one H plus on the right side. HCl is a strong acid, nitric acid is a strong acid, but we talked about ethanoic acid in vinegar. It's a weak acid, and this is going to form, we said, a weak electrolyte in water because it's a weak acid. These guys, these other two, will form strong electrolytes in water when dissolved in water. So we are building. On the other hand, the diprotic acids, di means two, they have two hydrogens to give. See, this breaks down, loses one hydrogen to give you HSO4 negative, one hydrogen is lost. Then put this here in the second step. This hydrogen can be lost to give you a second H plus, and the SO4 minus becomes SO4 2 minus. These are two protons in the original sulfuric acid. Now, the H2SO4 is a strong acid. This process is quite fast, but the second process is going to be slow. It's going to be an equilibrium. That is because HSO4 minus is a weak acid in the second step. So it's going to give you a weak electrolyte, while the H2SO4 is strong acid. It's going to give you a strong electrolyte. Triprotic acids, what are they? What are triprotic acids? Triprotic, twice means three. So these guys have 3 protons to give. And they tend to be weak acids, these ones. For example, the phosphoric acid breaks down to give you the first H plus and H2PO4 minus because you lost the H plus. You started with H3, now you have H2. Take the H2 dihydrogen phosphate, put it there. He loses one hydrogen, again it's weak acid, so it's an equilibrium to give out the second proton. Now losing that one hydrogen from the 2, the negative here is going to be 2 minus because each hydrogen is a positive. If you're losing it, you're going more negative. Now take these and make it lose one hydrogen. Again, it's a slow process. It's a slow process and it doesn't happen readily. So now the hydrogen that was left is gone. Now you have a phosphate at the end. So comparing the acids, H3PO4 is a weak acid, gives you weak electrolyte. H2PO4 minus is a weak acid, gives you a weak electrolyte. And HPO4 2 minus is a weak electrolyte. Weak acid gives you a weak electrolyte. So weak acid, weak electrolyte, weak acid, weak electrolyte, weak acid, weak electrolyte, strong acid, strong electrolyte, sulfuric acid. Weak acid gives you weak electrolyte, the hydrogen sulfate. Ethanoic acid is a weak acid, weak electrolyte. Nitric acid, strong electrolytes. HCl, strong acid, strong electrolyte. Here's a list of common strong acids and weak acids. As you can see, HCl, HBr, HI, nitric acid, sulfuric acid, and perchloric acids, those are the most common strong acids, meaning they're going to be strong electrolytes in solution. On the other hand, hydrogen fluoride, nitrous acid, phosphoric acid, acetic acid found in vinegar, those are weak acids, meaning they're going to give you weak electrolytes in solution. They don't completely ionize, while the strong acids will completely ionize, giving you the most ions in solution, helping in electrical conduction. Classify each of the following species in aqueous solution as Bronsted acid or base. We say that Bronsted acid is proton donor. Bronsted base is going to be the proton acceptor. Well, polarity will tell me. This has very strong dipole moment, making this hydrogen right here very acidic. So that hydrogen can be given away. This is a Bronsted acid. This has no proton to give. In fact, it's negatively charged. No brainer. This is going to be Bronsted base. This one has one hydrogen to give, even though this is a weak acid. HCO3 minus can do two things. He can give away that acidic hydrogen. The proton can be given away or lost to give you a carbonate, or the hydrogen carbonate itself can accept a hydrogen to give you, this is supposed to be reversible, to give you carbonic acid. So he can play the role of an acid, or he can play the role of a base by accepting a proton. So since he can play both roles, HCO3 minus is said to be amphoteric. So here the explanation goes in detail. You can see that HBr in water, it breaks down to give you H+. Someone else would say to give H2O+, but H2O+ just carries the proton H+ and the Br-. So if this is lost or provided to be stolen by something else, then we can conclude that HBr is Bronsted acid. It ionizes in water to give you a proton according to Arrhenius definition, but also that proton is now available to be donated away according to Bronsted definition of an acid, proton donor. And then for the nitrite, by virtue of the negative charge, it can accept a proton, meaning that the nitrite is going to be a Bronsted base to give you nitrous acid. That's what you see here. So nitrite is a Bronsted base. Hydrogen carbonate, like I said, hydrogen carbonate in water can give away a proton to give you H2O+ to the water. So the water is just going to take away this hydrogen basically, and the bond breaks to the carbon. You're going to get CO2-. So this is available to be donated. So that makes hydrogen carbonate or bicarbonate an acid, a Bronsted acid. But again, the same bicarbonate can accept a proton, okay, in an equilibrium equation to give you weak acid we call carbonic acid. You see now it started off H1, now it's H2. It accepted a proton. So that's why I said HCO3 minus the bicarbonate or hydrogen carbonate is really amphoteric, because it can play the role of an acid or a base. You see, you say that some animals are amphibians, for example, the toads or frogs, you should say. They can live both in water, they are aquatic, and both on land, they are terrestrial. So they are amphibians.